Hey guys, we're going to try to finish this up. We talked about this insulators, atomic, so there's where we did all those things at light principles. Talked about current flow, talked about the insulator, talked a little bit about light flow. No, that's not the one I'm on. So this will be the next, I think it's still under chapters. I've tried to come out and take the chapters off and put them under so some of the information in this link, the link says it's site report that you requested is not. Okay, so I need to check that. Undoubtedly, they do that every once in a while. So here's the key points in here. The water, the two carriers, electrical cables. So basically, we have two types of cables. We have those responsible for providing power, transmission power. Right? And we have the other ones that are responsible for, these are going to be metal. So we can't transfer power through fiber optic. So all your power cables or conductors are going to be metal. And in communication, these are going to provide electrical signals to electronic circuit. These could be either metal or fiber optic cables. Of course, what we're going to do here is we're going to deal with metal. Electrical power cables, of course, application of the flow, current, environment, ambient temperature. What's ambient mean? Surrounding, different installation configurations we're going to look at here. Okay. Electrical communication cables mainly use copper, or it's going to use some version of copper. A lot of times they'll tin plate them. So if you get a metal conductor, we talked about that, it might have a silver coating on the outside. Those are usually tin plated. And what do they tin plate for? To keep it from oxidizing, right? Three main categories. These are coaxial cable. I'll run into that. We'll look at that. This is using cable TV. It was originally the way we network computers together using coax. Now we use something called twisted pair cable, and we'll look at those. Coax is still used a lot in cable. It's still used primarily in cable TV, in high-speed communication. Twisted pair. So it's easier to make a lot cheaper. This was originally developed by the telephone company. The telephone company has been using twisted pair cables for years. Then we have two categories that we'll look at. We use twisted pair cables for wired networks. And basically we have two, UTP, which is unshielded twisted pair, and STP, which is shielded twisted pair. These are low frequency signals and low power dissipation, very small gauges. And then we'll look at what we call flat ribbon cables, also called ribbon. Fiber optic cables, we use these in communication, does not use metals. We have two that we use, glass and plastic. And what we'll be dealing with is we have plastic here, and we'll show you all that. Plastic is pretty easy to terminate. Glass is not. Glass is a lot harder to terminate and splice. These handles very, very high frequencies, but almost no power. I understand that. And of course, these guys are impervious to electromagnetic interference. So we already know what ampacity is. What's ampacity? That's the current carrying capabilities of a metal conductor, right? Neil, what's Neil? So when we heat a metal up and cool it down at a real slow rate, it makes it softer and it makes it more malleable or easier to bend. Buffer, what's a buffer?
Not in here.
Buffer is a go-between. Characteristics impedance, we hadn't talked about that. Circular mills we have. We hadn't talked about cladding. Coated wire, I don't know what that is. Core, DB. Some of y'all have heard of DB, but odds are you have no idea what that is. So we need to understand what DB is.
Just did a fiber optics test and everything was measured in 45 dB.
Yeah, DB, we'll look at that. We'll talk about that. So understanding, most of the time when we have loss in a communication cable, they use dB. They don't use volts. They use dB. Because what happens is that the voltage of a cable. So it would be hard for me to say, okay, I'm going to lose this much voltage because communication cables carry different voltage, right? But if we knew the dB loss, we could calculate the maximum dB loss. We could calculate the voltage drop loss over that cable. Ductile, extrude, hard drawn, and hydroscopic. What's hydroscopic? Term KC mill, also called MTM. We okay? Low voltage, malleable. We're going to look at these. Medium voltage, mode, non-oxides. We already looked at ozone. Plenum. Anybody know what plenum is? The plenum is the space between an artificial sealant and the true sealant. So that space between that's the plenum. Yeah, it's a drop. It's the distance between that. So we're going to have what we call plenum rated jackets, which means these guys are designed to run up in the plenum. If it's not plenum rated, it means you're not supposed to run that thing up in the plenum. Because RG, we'll look at RG cables, soft drawn, thermoplastic, thermoset. I think we already talked about thermoplastic, thermoset, right? Undercoating and vulcanization. Some of these we already talked about. So basically, we have two types of metal conductors. We have solid and we have stranded. Hard drawn means what we do is we literally take the metal and we don't do anything. We pull it through a series of dies. And each series of dies reduces the diameter of the wire. That's called hard drawn. Soft drawn, we do heat it. And then we cool it to remove internal stress. Soft drawn metals has low tensile strength, high elongation under stress, and usually used in dope. So most of your network cables are going to be soft drawn, which means if you put them under stress, they're going to stretch and it's going to change the gauge, right? You know what I'm saying? So we'll find out we have what we call cables that are riser cables, which means they're designed. These guys are probably hard drawn. They're going to be a little stiffer, but they're not going to elongate as much when they're under their own weight, right? That makes sense. Of course, we know that silver is the best conductor for electricity. Used as plating on contacts. Used as the plating on some conductors. Used in silver solver, very expensive. Copper is probably the most widely used conductor out there. The two most widely used are what? Copper and aluminum. Of course, we know gold is the third best. We've already talked about that. Aluminum is the fourth best, but it's strong, light, and cheap. High voltage transmission lines used for some lower voltage power transmissions. And until recently, it was used in integrated circuits. The problem we had for years is that silicon and copper did not get along with each other. Silicon would literally dissolve copper. So when they made printed circuit boards and they used silicon, if they made their conductors out of copper, they would eat up. So they had to use aluminum. Aluminum and semiconductors get along real well. So they finally came out with a technique where they could coat the wafers, and then they'd run the copper above that. And Intel called that processor the copper mine, by the way. I forgot what number it was. Intel gives these microprocessors names while they're under development. Other conductors: brass, zinc, iron, and nickel. Tungsten. Basically, tungsten is a metal, but it's more like a resistor than it is metal. Nichrome. We use nichrome in electric heaters. And of course, this is some advantages and disadvantages, right? So it has better, it's going to corrode, it's better than silver. Aluminum is what? Cheap and light. Doesn't get along with copper. But the problem we have with aluminum is that it corrodes and expands and retracts with temperature, right? And we know what an alloy is. What's an alloy? It's a metal that's produced by the mixing of other metals, right? And silver and gold are used as platings. And we already know this. I'm just so a lot of this is a repeat. And we looked at the American wire gauge. In fact, this is all a repeat. What we're going to do is I'm going to go through this. We've already gone through these. There's all the KC mill conversions that we did. We worked all those problems, talked about ampacity, talked about insulation. So this is the basic construction. So these are our basic insulators we have. We have rubber, we have elastomers, thermoplastic, thermosetting, nylon, Teflon, mineral insulation, paper, varnish, polypropylene, silicone, Teflon, so these are different. In commercial and residential wiring, thermoplastic and thermal setting are the two most widely used. In communication cables, you're going to run into these other ones. Okay? So that's something you don't have to memorize. Jackets. So we have two things. We have what we call an insulator. What's the function of an insulator? Huh? Yeah, but why do we need to do that? So it allows us to bring cables together, right? You understand? So they don't short each other out, and allows us to do what? Hold them, handle them. That's what we use insulators for. Keeps that push in instead of it getting into me or getting into another cable, right? Huh? What's that? Yeah, it allows us to handle the conductor without, it allows us to bring conductors close together. Right? You understand that? What's the function of the jacket? Protect the conductor from the environment. Okay, you understand it? The insulator and the jacket can be one unit. But when we get into cables are definitely going to have jacket on. So this is a medium voltage. This is the basic construction of a medium voltage cable. Now, what's medium voltage? So what's high voltage? What's medium voltage? What's low voltage? No, you're talking current. We're not talking about. Yeah, what's the actual values of low current? We hear that term all the time: low current, high current, medium current. So basically, I'm sorry, high voltage. We're talking about insulator. High voltage, medium voltage, low voltage, medium voltage, and high voltage.
You would think that AC
Okay, would Alabama Power would consider to be low voltage, high voltage, and medium voltage?
No, that's just the low.
No, no. And what you got to understand is that those meanings have different meanings depending on what you're dealing with. So low voltage for Alabama Power might be around 2,000-3,000 volts.
Yeah, but the high voltage might be in 100,000.
Yeah, and high voltage might, right. Now NEC, National Electrical Code, says low voltage is 120 volts, high voltage is 240.
Yeah.
Right, you understand?
That's for residential.
It's residential, it's not for commercial use. So when we use low voltage and high voltage, this would be construction of a sure enough high voltage cable. And I think I tried to go in and give y'all some of the specs inside that handout when I define high voltage and low voltage. So high voltage and low voltage basically depends on its application. What field are you in as far as getting electricity down?
It's high voltage in residential.
Yes, 240 in residential.
So you got to be very specific on
what you're talking about. That's exactly right.
Not people are
I thought I had a section in here. A low voltage. So IEC identifies low voltage as 1,000 volts AC. Greater than 1,000 volts AC or greater than 1,500 volts DC. IEEE says low voltage is less than 1,000 volts. NEC says relative to electrical power 0 to 49 volts. Electrical power, right? And then NEC definition of NEC is 2,000 volts AC applies to cable construction. And then, of course, here's medium voltage. So medium voltage, it all depends on where you're working at, right? You understand. Residential wiring, we get into residential applications, then low voltage would be 120, high voltage would be 240. I get into commercial applications, then it's going to change depending on if I have 3 different voltage levels. The smallest one is going to be low voltage. The one in the middle is going to be medium voltage, and the highest one available. So what US Steel calls low, medium, high is going to be different too. So it all depends on where you're at. These are defining the instructions of transmission lines, is what they are, if we insulate them.
Here we consider high voltage 480.
480, if that's the highest voltage that they deal with. Right, and you find that, and that's very, 480, 240, and 120 are very, very common in commercial applications. I think the highest voltage US Steel had was around 6,000 volts. That was their high voltage out there, if I remember right. They had 2,200 out there. So they had several different voltage levels. And then they had shops that might have 240, 220, 440. It all depends on where you were at, what would be considered out there. So when you get into industrial applications, your voltages are going to be all over the place. So your high power units out there are going to be operating at a pretty high. It's going to be operating at the highest voltage that's available. So it all depends.
Yep.
So this would be construction of a medium voltage cable. And of course, that the book that we were using at the time specified. Now the problem is, the next class probably explains this. Anytime we get a conductor up against a piece of metal or even another conductor, what happens is your stress moves to one side. So that means if I've got an insulator that's rated at 600 volts, then what that means is that's 600 volts, but that 600 volts is equally around the insulator. The problem is I take that cable and I flop it down on a piece of metal, then all my stress moves over to that piece of side. So if that sucker was rated at 600 volts, And now this is 600 volts, and it's going to push through the insulator because that 600 volts is supposed to be distributed around the outside of the cable, right? You understand that? That side part of the insulator could break down. So we could actually get current flow through there, and once you get current flow, then you create those carbon paths through there, and then you got a big problem, right? You understand? So when we start getting into these high voltage cables, they try to do something that makes that insulator see this no matter what you're up against. So what they start doing is they start adding components to the cable. So notice what we have here. We have the actual conductor itself. And then what they do is they take that and they surround it with what? A semiconductor. So what the semiconductor is going to do, it's like a resistor, so it's going to have some more current flow than the insulator does. But what that's going to do is going to equalize the pressure around that conductor. Then we have what? Then we have the insulator. And then what we do is we put, then when they get into these high voltage and medium voltage cables, they actually put a shield around the thing. So that shield is around it. So what's that going to do? It circles the whole thing, so it's going to concentrate, even out, right? You understand? And then we run into the actual outside jacket. So we call this a cable. Now, so we say a cable, I was under the impression too that a cable had to have two or more conductors in it. And then I'd hear the term cable all the time, and I realized they use that term for cables that are constructed with multiple layers. So James, turn over and get that big old cable over there. The one that's got the terminal on it. Yeah, it was the one that y'all did, the big wire gauge. The one we did, the big wire gauge.
I already paid $60 a month, so double, but more than double.
Everybody okay here? Now these would be, I'm sorry, this would be, yeah. Everybody understand, this would be a medium or high voltage cable.
Yeah.
According to Alabama Power, not according to house wiring. This is well, then you got industrial, you got power transmission, you got industrial, you got in commercial, and you have residential. And in each one of those fields, the definition of a high voltage and low voltage is different.
Yeah.
Especially in industrial applications, because industrial applications, they might have more than 3 voltage levels available. So it depends on where you work. Now, even companies that are versed in interstate power might have a different, interstate power might have a different than intrastate power voltage levels as related to residential power transmission or distribution. We're not talking about when it gets to the house. So even those 3 levels might have different levels. So intrastate means, of course, interstate means you go between states. So Alabama Power has power lines running between states. And so a lot of times they'll actually sell power to another power company, depending on when they need or when they don't need. Intrastate means those are your lines that are not intended to go over extremely long distances, and they got limits. And then you have the distribution, which would mean that's after they go through and come out through the residence. They have different, what would be considered high, medium, and low voltages. So it's really a arbitrary number. This cable right here, I don't even know. This probably cable here, I think would probably be, we had a video too where a guy was talking about the transmission power and the voltages that they use for interstate, interstate, and local distribution. I wish I could find that. It's probably in the folder somewhere. But what voltage level this would be, I know this would be at least medium voltage transmission, insulated. So this would be like a cable that would be running from a transmission line down to a building. A coaxial cable. This is where we start getting into communication cables. And one of the main communication cables we have is what we call coaxial cable. A lot of people just call it coax. I've heard of coax, but the technical name is coaxial. And it's going to consist of a jacket for the environment. It's going to consist of some type of braided for strength. And then what it's got is it's going to have, this is going to be an insulator. And then we're going to have a shield. This is multi-layer. I'll show you all this in a minute. This is standard cable. But let me explain something first. And we're going to shift to another PowerPoint. When we're talking about signals, signals might be DC signals, but they're definitely going to be, they're either going to be AC or DC, but they're definitely going to be changing. Anytime I start changing where the current actually varies real fast or varies, then we're going to be dealing with what we refer to as reactance. We touched just a little bit in that. So anytime I have two conductors that are in close proximity to each other, we create, and they're insulated by something, we create capacitors. Anytime I have loops in a cable, we create what we call inductors. These guys create an opposition that does no work. They literally don't do work, which means they don't get hot. But what they do is they cause loss of signal in our signal. What we'll find out, and this is what we're going to find out on this slide, is we're going to look at something called impedance matching, and then we can understand our coax cables and our other communication cables. And of course, this is a basic review. These are some formulas that you should start learning. Most of y'all should know that. The one on the left is what we call Ohm's law. Notice I've changed the R to ohms. So all opposition to current flow is in ohms. Whether it's resistance, whether it's reactance, or whether it's something we call impedance. Everything's in ohms. And anytime you have ohms, you have signal loss. Everybody understand that? Then we have what we call power. Power, of course, is the rate of doing work. And we have two types of power. We have what we call apparent power, and we have what we call real power. Here we're in transmission. Transmission wires have to handle apparent power. In AC, you'll learn exactly what that is. But what we have is we have components that do no work, but they appear to be doing work. So if that means if I got an ammeter and I have a capacitor, I would measure a voltage drop across it, and I would measure a current flow in and out of it. My meter don't know if it's in and out or through. My meter has no idea. But what's happening in the capacitor, if you picture two buckets, then basically that's what a capacitor is. So if I was to, and I got a PowerPoint somewhere, I'll try to find it, probably in AC. So if I had two buckets over here, and then I had a pump, and then I have a resistor, and then what my pump is doing is it's filling if it goes in one direction, it takes water out of this one and puts it into that one. Now the current flows through the resistor. The resistor does real work. And then it would fill this one up, or start to fill this one up. But then after a while, what AC would do what? It would change directions and it would move back over there. Well, what you probably notice is these buckets are filling up, but there's no current flow through the bucket, right? You understand? And that's what a capacitor does. That's what a capacitor does. And that's what inductors do. There's really no AC current flow. There's really no AC current flow in them. But if I'm over here and I'm measuring flow, I'm measuring the flow into that bucket too. So it appears there's current flow into the capacitor. And it appears there's current flow through it, but there's not any current flow through it. So if I was to take the V times I and measure that, not only would I be measuring the current flow through the resistor, but I'd be measuring the current flow in and out of the capacitor. Well, the capacitor's doing no work. So what this does is this creates a type of power we call apparent power. And we pay for apparent power. So we have two types of power in an AC circuit. We have apparent power and we have what we call real power. This is the R. This is the resistance in the circuit. And this is the actual work you're getting. Now we have methods where we can compensate or adjust apparent power back into real power, but all your conductors have to handle apparent power. Y'all understand that? So that's why the APP, this is apparent power. Real power, we also call that true power. And what we end up with is we end up with a fraction called the power factor. We can calculate the power factor in two different ways, but one of the way would be, we would come over here, it would be the true power divided by the apparent power. I'm going to spell apparent wrong. Apparent. This gives us a fraction. If you had a power factor of 1, it means you have no reactive power. If you have a power of less than 1, that means you're paying for more work than you're getting. And that's when we start getting apparent power. So we have to worry about this in AC. We don't have to worry about this in DC. We get into three-phase power transmission, then what we do on three-phase, remember three-phase, your power is spread out over 3 wires. But they're not equal. So if I came over here and measured the current through here and I measured the voltage through here, if I measured the voltage between phases, then what I would get is I would get the power being delivered by 1 conductor, but the power is being spread out over 3 conductors. So this deals with some trigs, by the way, but it comes out to be the tangent. But we're not going to talk about that, about an angle. But this is what's easy to remember. Since it's 3-phase, you just multiply everything by the square root of 3, which is 1.73. So that means if I measured the current in 1 conductor and measured the voltage drop across the conductors and it came up with something, then to get my total power being delivered by all 3 wires, is you'd multiply that by the square root of 3 if you add them together. So that's the 3-phase formulas change a little bit from our actual formulas right here. Now this is dealing with power transmission. When I get into communication, we're going to deal with something called impedance matching. Communication conductors are used to deliver power, and communication signals are both. That's uncommon. We do run in that. So if you've got a wired telephone, you have 2 wires running to your phone. Yet it can have lights on it. It can do all this kind of stuff. So what the telephone company does is those conductors are used for 2 different things. It's used to not only deliver power to the phone, so your phone don't plug in, right? You understand? And it's also used to send voice through there. When we get into networking cables and stuff like that, and that's not true either. We've got, instead of using, in our college, we're using what we call voice over IP. So what we're doing is we're sending telephone over regular networking cables. And these phones have to be powered. So we got what they did here at the college is they actually used 2 of the conductors in the network cable to power the phones up. But if I was to run it through a switch, then my phone wouldn't work unless we had an external power port. So that's another one. So voice over IP, we can do that a lot now. So I can get on my cell phone and I can call a wired network. I can call a wired phone over my cell phone. Well, my cell phone uses what we call an IP address. The way But somewhere down the line, the telephone company comes over and takes that voice over IP and converts it over to voice over wires, right? You understand that? Which is pretty neat. So, are we okay? In DC circuits, the opposition to the current flow is set by the resistance of the source and return conductor along with the load. In AC circuits, the opposition is set by something called resistance and reactance. So reactance varies with frequency, resistance does not. Now, when I come up here and I combine reactance and resistance in the circuit, it creates an opposition that we call impedance. In formulas, we represent this with Z. And your own law formulas are the same. This would be, Z would be equal to, what's Ohm's law for R? V over I. Well, this is also true over here. So Z would be equal to V over I. It's still the same formula, except this would consist of apparent power. And what you'll find out is that people deal with communication cables, they'll start talking, you'll hear the term impedance a lot. In fact, a lot of people, if they're dealing with AC, they'll use the term impedance, whether it has resistance or a reactance in it. To some degree, everything opposes the flow of current. Everybody understand that? A regulated AC to DC power supply source appears to have an impedance of practically zero, as long as the power supply design parameters are exceeded. So regulated power supplies, what they do is if you try to pull more energy out of it, they put more energy in. Every AC or DC signal source will have an internal resistance or impedance. An internal impedance causes the voltage produced by the source to drop when the load is down. Power is work, not current and voltage. Everybody understand that? So we can't have work. So what is work? So if I go out there and push a car and the car don't move, do I do any work? No. Car work is force over distance. So to do work, something's got to move, right? You understand that? So we cannot have work without push, and we can't have work without motion. Now, in electricity, our push is our voltage, right? You understand? And your motion is your current. Anytime I push current through any type of opposition, we get a voltage drop. Every source of power has an internal resistance. So if my power supply tries to provide a current, it will drop a voltage. Now what regulated power supplies do, if the voltage tries to drop, they put more energy into the power supply and it appears to have 0 ohms. It appears, but it don't. They're compensating for the internal resistance. Signal sources don't have that. So as soon as I load a source of a signal down, it's going to drop. You understand that? We don't regulate signals. We don't regulate power. And this is what happens. This is why when we have shorts on a regulated power supply, it flat will burn stuff up because it keeps pumping more energy in as long as it can, right? You understand? The primary goal of a communication channel is to get the maximum power from the transmitter to the receiver. Trying to get the maximum power between the transmitter and the receiver. Y'all understand that? Everybody follow this so far? So impedance matching. The power transfer between the transmitter and the receiver is maximum when all the impedances in the circuit match. Every signal transmitter has some impedance. This causes the output signal to drop when they're connected to a load. In this example on the next slide, the resistance of the source is 100 ohms. And what we're going to do is we're going to vary the load resistance. Y'all need to get y'all's calculator out. So what we're going to do is we're going to simulate it. We're going to use DC. We're not going to use AC. Just with DC to get y'all feel of that. So what I'm going to do is I'm going to start off with a source that's got 100 ohms worth of internal resistance. And then I'm going to attach a load of 10 ohms. I'm going to attach a load of 100 ohms, and I'm going to attach a load of 1,000 ohms. Now what we're doing is we're trying to learn this, why we use coax cable and why we use twisted pair cable in a communication. Yeah, and then we're going to put, so here's the circuit. So here's my circuit. So this represents the signal, this represents an AC signal. This is my source, and it's got 100 ohms worth of internal resistance in this situation. And what I'm going to do is I'm going to come up here and I'm going to put a different load in. Yeah, and what we're going to do is we're going to calculate the power to the load. So what would be my power to the load? Well, the easiest formula to use here is what we call the voltage. You can do it with Ohm's law. So Ohm's law said I would take 10 volts. I would divide it by 110 ohms. That would give me my current. I would take that current and then I would do that to calculate the power in the load. We have another formula that we call the voltage divider formula, where you can calculate voltage drops without calculating current. So the voltage divider formula says I can calculate the voltage drop in any series circuit by taking the size of that resistor and dividing it by the total resistance, and then I can multiply that times the applied voltage. So our applied voltage is always going to be 10. So we'll say Rx, V, if I call that R1, VR would be equal to 10 divided by 110 times 10. Now what this is going to do is this is going to give me a voltage drop.
Yeah. 0.91.
Okay. Now what we could do, we got that. We could take that and divide that by 10 ohms to get current. Then I could turn right back around and multiply it out, but we don't have to do that. Another formula that we have for power is equal to V squared over R. So what I can do as soon as I do that, I can square it and divide it by R, and that would give me my power. So we can do this with basically one calculation. So it means I'm going to take the 0.91, I'm going to square that, and I'm going to divide it by 10, and then this will give me my power.
0.91 gives you 0.8281.
Yep. And we're going to divide that by 10. 800 in
0.08.
milliwatts. Okay. So what we're going to do is, so when would you think we would get the most power transfer? At 10 ohms, 100 ohms, or 1,000 ohms? What do you think? When do you think we get the most power transfer to the load? What do you think, Dave? What do you think, Thomas? Come on. Say that. You're either right or wrong. It don't count. I mean, this is 1,000. Okay. Okay, here we go. I'm going to put that in here. Here's the math. So 82 milliwatts. Okay, everybody okay? Okay. Now we're going to pop that out, and we're going to bring 100 ohms. Y'all like my animation?
Oh, yeah.
Of course, I didn't put 100 ohms. Dang. This is 100 ohms. For some reason, my 100 didn't come in. Calculate 100. So this is going to be 100 divided by 200, which is 0.5. Square that and divide that by 100.
250 milliwatts.
But it went up.
Yeah. 1,000.
Okay, here it is. So 250 milliwatts.
Yeah.
Okay. So notice it went up. So most people say 10 ohms, by the way. 250 milliwatts. Okay, now let's do it for 1,000.
So 100,000.
Y'all gonna be surprised. So none of y'all got it right. What is it again?
Kind of messed me up.
Yeah, I'm looking at this. So 100.
No, it's gonna be 1,000 divided by 1,100.
And then
Square that and divide it by 1,000. So, 82. It's gonna be back down to 82 milliwatts again. So it's back down to 82 milliwatts. So when did we get the maximum power transfer? When when the resistance of the load matched the resistance of the source. And we call this impedance matching. No, nobody said 100. James said 10. Both of Jameses said 10, and you said 1,000. 100 ohms, and we just got through doing that. So what does it say? Right? What did we just say up here? What did I say? Right here. No, right. All through this animation. Let me go back to that. The power transfer between the transmitting source and the receiver in a such circuit is maximum when the impedance is in the circuit match. So what we do in communications is we don't let the impedance arbitrarily be set by just a cable. We build the cables with a certain impedance. The cables are built with a certain impedance. The transmitters are matched to the cable. The cables match to the receiver. If everything in a communication system has the same impedance, you get maximum power transfer between the transmitter and the receiver. Good catch.
Yeah.
Y'all see that? I wish I had that on video.
I almost don't believe it. That was
Don't do it again.
pretty good.
So what we do is we set up cables, coaxial cables, and twisted pair cables have a certain impedance. And if my transmitter has that impedance, and my receiver has that impedance, and the cable has that impedance, we get maximum power transfer between the transmitter and the receiver. Huh? Everything matches. It's just like, and this is true only in communications, though. So in communications, we don't arbitrarily choose these conductors. So I had my father-in-law. He had his cable. He had this big old truck that he was pulling in his backyard, and he hid his cable, dropped down from his TV. Hid his cable, broke it. Got him a big old ladder, pulled it together, twist the wires together, and he couldn't understand why his picture was so crummy. Well, he screwed up the impedance of the cable. So now the impedance in its system did not match anymore. Right? You understand? People come in and they try to use, he tried to use the screen on his house as an antenna for his TV. Got a crummy picture. It picked it up. He thought what you was looking for is surface area. You're not, especially transmitting. Transmitting is what's really critical. And so we have what we call, so impedance matching is very, very important. So what we do is we set these cables up. So let's look at a coaxial cable, and let's look at it with a lot of detail. So what we have on a coaxial cable is we have a conductor, we have a insulator, And they call it a shield, but it's not true shield. We have another conductor. So what do we have? Well, we have a capacitor. A capacitor has an impedance. So what we end up with is we end up with what we call an equivalent circuit, which basically ends up, this is the symbol for inductors, this is the symbol for capacitors, and this is what we set up on a coax cable. And what's so neat is that this capacitor, if we hook capacitors in parallel, they add, and then inductors cancel capacitors out. So what this ends up with a cable that has the same impedance no matter what the length is, which is really cool. So if I've got a 75 ohm coax cable, that's impedance. You cannot measure the impedance of a cable with a meter, because a meter puts out DC. Impedance is AC, right? You understand? So we can't measure the impedance of a cable. We had a little test jig that we set up where we would come up and we'd read the voltage on here and we'd switch different impedances. And when we got the maximum transfer on there, we would look at what we had said, and that would tell us the impedance of the cable. You cannot measure the impedance of the cable with an ohm meter. All you're going to do is measure the resistance of the cable. So this is something called twisted pair, which we use in networking, and this is the equivalent circuit of a twisted pair cable. But it also has the same characteristics. But I think the twisted pair, to get on twisted pair, I think the minimum length of the cable has got to be at least 4 feet. But above that, it don't change. But if I've got a cable, so if I have a 75 ohm coax cable, and then I hook this up and my transmitter's got a 75 ohm output, and my receiver's got a 75 ohm input, then everything in the system matches, and now my cable company can transmit maximum power between the transmitter and the receiver. Now, if my transmitter had zero impedance, then we could basically send infinite power, but we can't do that. Every signal source has an internal opposition. We can't regulate that, right? You understand? If I regulated, I would be really screwed. I mean, I can look at a cable rated at 100 megabits, and we're sending gigabits over there. I mean, rated at 100 megahertz, and we're sending billions of bits per second on there. Well, how can we do that? Well, they're doing something called quadrature amplitude modulation, which they're changing not only the bits, but they're also changing the amplitude. So I cannot regulate the amplitude if I'm using the amplitude to represent the information, right? You understand that? So when I send information, normally what we do is we do what we call modulating. We'll talk about that. So in a communication system, every signal transmitter has an internal impedance. Every conductor has an impedance. Every load has an impedance. Maximum power transfer occurs when all these impedances do what? Match. So instead of arbitrarily choose it, we choose a certain cable. Everybody understand that? So that we got in networking, we use what we call RG58. And it's got /U58. What they decided to use in cable TV is they decided to use RG59. Are those two compatible? What's the difference between them? Besides for size. One of them is 75 ohm, one of them is 50 ohms. So RG58 is 75 ohms. This is what we used to use on networking all the time. RG59 is 50 ohms. But we couldn't match, so I couldn't take, if I had a roll of RG58 and I wanted to run cable TV through my house, I just screwed up. Now my pictures are going to be crummy because why? I've screwed up the impedance matching. So we got to be really, really careful when we splice these things. Our coax has to be spliced. We just can't strip them and put them together anymore. We have to run through splices. When we get into twisted pair cable, we really, really got to honor stripping these things, how far we get them out of the twist and all kind of stuff, because all the twist in a twisted pair cable sets up the characteristic impedance of the cable, right? You understand that? So I've seen people do networking, and they'll take those things and they'll unstrip those wires back a long way, and then it'll run, but instead of running at 100 megabits, it might run at 10, because what Ethernet has done is they've made everything downwardly compatible. So the first networks that we used were 10 megabit networks. And then when we went to Twisted Pair, they started off at 10 megabits, and then they went up to 100, right? You understand? But they're still downwardly compatible with what? 10. And what your transmitters and receivers do is they try to communicate at the highest speed, and then they automatically do what? They start dropping down until they get a link. They can get a link. That's been true for a long time. So coaxial cable, we have different coaxial cables, and I think I've got a chart on here, and it's not going to be in the one that I've uploaded, guys, because I just put this in there today. I realized that I keep going right past it. Slow down, Rick. Slow down. Nope, that's not the one. Where's my other PowerPoint? So these are the different cables. Now look at another thing we need to learn about.
Why is there two different DBs? One with a capital D and one with a lower D. What does that mean?
Don't mean anything. Looks like a one of them is 10 megahertz, the other one's 100 megahertz.
So there's really no difference.
But these are the different categories. Y'all can't see these, guys, but this is RG58, and it has a characteristic impedance of 50 to 55 ohms. But this would also be RG8, this would be RG17, this would be RG19. And you can see what's varying is the diameter of the wire. We're using inside our cable TV, we're using RG59. Out there on the cables, they're usually running RG6, I think, which still is a 75 ohm cable, but it has a bigger diameter. Maybe I'm wrong. So this is about a 1/4 inch. The RG59, which is what they bring inside your house, is only about 146 milliinches. But see, what they're doing is we have several categories within that range, right? You understand? But then they still got to handle a current. So that means I could have a 75 ohm cable that's got 75 ohm impedance, and then it might have so many ohms per 1,000 feet. Well, when I start pushing signals through ohms, it's going to drop the voltage too, right? So what we would do, if I got to send it over a bigger distance, I could still use a 75 ohm impedance cable, but the cable would be bigger. Does that make sense? So if you look at the cable that drops down, that they actually run all the cables with, it's going to be a bigger gauge cable, but it's still going to be a 50 ohm cable, impedance, right? You understand that? So get the difference between impedance and resistance. They're two different things. So impedance comes into play on AC, right? You understand? And resistance is strictly what? It could be AC or DC. Now, I know y'all can't see that. I'm sorry. So what do we need to talk about next before we get into communication cables? And also fiber. We need to learn a little bit about what DB is. Anybody know what DB is?
Is it still a decibel? Is that what it means? Or
Yeah, that's what it means. It stands for decibel. What is it?
That's more than just sound.
Well, originally the DB was developed for audio. Yeah. Because our audios vary in dB. So basically, a doubling in power does not necessarily mean a doubling in volume. So what we have to do is we have to go in what we call powers of tens. Y'all familiar with logarithms? What are logarithms? We have two. What are logarithms? So our calculator has the ability to do logarithms, not algorithms. Algorithms is a step-by-step we use to solve problems. Here we're talking about a logarithm. So what is a logarithm? So in communications, so Alabama Power calls their loss line loss. In communications, to determine the loss, the power loss in the cable, we use something called dB. Originally it was set up for audio, but now we use it just about any communication system, we use the term dB. But dB uses what we call logarithms. A logarithm is some fixed number raised to some power. And we have two, we have one. So exponents are made of two things. It's made of what we call a base, and then it's made of what we refer to as an exponent. Logarithms have fixed base. We have two fixed base. What is the gain in attenuation? What is a bell or decibel, right? What is gain? Yeah, so in communications, we'll get more out than we put in as far as power goes, right? Now understand, we can't create power, but we can manipulate it. What is a bell? You know what a bell is. So let's talk about that. So gains are calculated as out divided by in. So power gain would be power out over power in. Voltage gain would be voltage out over voltage in. And current gain would be current out over current in. Your primary gain you're looking for is power gain, because power is work, right? You understand? If an amplifier, so what would be the voltage gain? So voltage gain says, okay, I have an output of 5 and I have an input of 0.1 or 100 millivolts. What would be the gain? Get out your calculator and let me know. I'm going to say 5 and I'm going to divide it by 0.1. So what would my gain be? 50. 50 what? No, we're not even to dB. 50 is a multiplier. And this gives people problems. I'm talking about voltage gain, and for some reason they want to give this multiplier voltage. They want to give it some type of unit. Gain has no unit. It's just like I said, okay, I'm going to triple your salary. And he says, oh, that's great. I'm going to get a $3 an hour raise. No, you don't understand that. So that multiplier, that's a multiplier. So that means now if I understand the gain of a system, I say, okay, if I put if it's got a gain of 50, if this amplifier's got a gain of 50 volts, a gain of 50, not 50 volts, that means if I put 2 millivolts in, I'm going to get 100 volts out, right? You understand? If I put 20 millivolts in, then I would get 100 millivolts out, right? You understand? And that's all a gain is. A gain just tells us, or if I'm getting 50 volts out, it means I had to put 100 millivolts in, right? You understand? So if I know the gain, I can either calculate the gain that it gave, the input that's required to produce that output, or I can calculate the output I get if I put a certain input in. Fractional gains mean there is a loss in the system because the output is less than an input. What would be the power gain if if the input to a system was 8 watts and the output was 5.6 watts? So my gain, by the way, in formulas, I don't want to use P. So for some reason in formulas they gave A to mean gain. Yeah, so P would be a power gain. So I'm gonna come over here and I'm gonna say, okay, what's my output? My output is 5.6. My input is 8. So what is my gain gonna be? We call it a gain though. The formula, the gain formula does not mean you get more out than you put in. It's just a formula. So what would we get?
0.8.
And what's that unit? No unit. Gain has no units, right? You understand? But here we don't actually have a true gain. We have a loss. Technically, we refer to losses as attenuation. But it don't, the gain formula don't change. No, no, it has no unit.
So the only way you can represent
Well, we could use milli, we could use micro, we could use nano, but that's not even a unit, right? You understand? That's a way of representing large numbers with few digits.
Yeah.
And dB. That's what dB is. So dB is not a unit. dB is just a method we can represent large or small units with few digits. That's all it is. So dB is just another method. We use engineer notation.
That's part of
Well, dB is not part of engineering, but it's another method. Okay, are we okay? All right, there's a unit, 0.82. Gains are multipliers and have no unit. If you know the gain and the input to a circuit, how can the output be calculated? Well, your out would, so if gain is equal to out over in, right? You understand? We can put it inside that magic wheel that we learned, right? Out over in, then what? Out would be equal to gain times in. In would be equal to out divided by gain. And gain, and of course, gain would be out over in. So we can do the same thing. Anytime you have an equation that's got 3 terms in it, you can put it inside that. I've seen it inside wheels. I've seen it inside triangles. It don't make any difference. I usually don't draw anything. And I can put it inside that. And I can transpose an equation without using algebra. An amplifier has a gain of 0.23. What would be the output to of the amplifier if it's got a gain of 0.2? Yeah, I'm sorry, if 0.2 volts are placed on the input. So here we're calculating AV. Yeah. Yeah, so gain has an amplifier. I'm sorry. So here we're trying to calculate out. So what would out equal to? So out, and here we're dealing with volts, would be equal to what? Out, which would be what? 23, I'm sorry. So my volts out would be equal to what? 0.2 times what? 23. So I can't call this. I got to call this V out. 4.6 volts. That would be volts, right? An amplifier has a gain of 45 watt. Amplifier input voltage will cause 7.2 volts to be measured on output. So this is VN. So this is going to be what? 7.2 divided by 45. Volts. Are we okay? Are we okay? So all your gains are always what? Out over in. Power gain would be P out over P in. Current gain would be I out over I in, right? Voltage gain would be V out over V in. So there's gains. If a signal passes through multiple gains, the gains are multiplied together. So it's just like if I tripled your salary and triple your salary, I'm not increasing it by 6, I'm increasing it by 9. Right? You understand? So if I was giving you $1 an hour and I said times 3, that's going to give you 3. And then I say I'm going to triple your salary again. Well, that's going to be 3 times 3, that's 9. A lot of people, you say gains are added together, but gains are not added together. Gains are what? Multiplied. Y'all understand that? So we could calculate the entire gain of a system by just multiplying the gains together. Now notice here, this is not a true gain. This is an attenuation, right? You understand? But if you knew all the gains and all the losses inside your system, you could literally calculate what you would get over here when you put something over here, right, in a communication channel. The more consecutive gains, the more complex the math. So we're not going to do these problems. Attenuation, fractional gains create an output that is less than the input. This is often referred to as what? Attenuation. In power communication meaning, attenuation is also defined as the loss of signal strength over distance. All media has attenuation. Attenuation is also introduced in splicing termination. This is what we try to prevent. So we can control this, right? You understand that? So this is a bunch of math. Here we go. Exponents consist of 2 parts. What's the 2 parts? So x would be what we call what? The base. And what you raise it to, we call that the exponent. Everybody okay? This is called scientific notation. We can represent any number in scientific notation. In fact, most of your calculators, when you exceed the range of your display, they automatically jump into what? Scientific notation. For as soon as we start doing that, we lose some accuracy because we're still displaying the same number of digits, right? Everybody okay? Yes or no?
$1.
Huh?
$1. $1.
No, it's not. It's 12 o'clock.
Hunting.
So longhand methods, I could say, and by the way, when we multiply exponents, all we do is add them together. So I could come up here and say, 3,125 times 25, I'll come up in that number. Or I could come over here and say 5 to the 8th, and I would come up with the same number. So when we multiply, when we do exponents, all we can do is just add their, y'all understand that? So that's why things are given in exponents. It's a lot faster to do gains and attenuations because all I have to do is just add the exponents together. Everybody understand that? Pretty sweet. And then, but sooner or later, I'm going to have to take it and raise it to some power. Logarithms are numbers represented by exponents that use a constant base. So we have 2 types of logarithms. We have what we call common logs and we have natural logs. So natural logs are things that vary in curves, or what we call exponential curves. So we don't need this guy. So everything we're going to do is going to be a common log. So dB is in common logs, right? You understand? And dB is always the exponent that we're going to raise 10 to. In communication and power, common logs is used. Everybody understand that? Are we okay? A common logarithm is 10 raised to some power. The power to which 10 is raised to is called a bell. So if I had 10 raised to the 5th, this would be 5.256 bells. So now I can give it without giving 10 because 10 is understood, right? You understand? Yes or no?
Yeah.
That makes sense.
Yeah.
So logarithms is nothing but what 10 common logs are nothing but what 10 would be raised to get that number. That's all a common log is. So if I come up here and put in my calculator and I put 100 and I hit log, so where's log at? right here. I'm going to put 100, and I'm going to hit log, and it's going to say 2. It's 2 bales, right? You understand? That would be 2 bales. If I come up here and put any number up there, I can represent any number with a logarithm, but it's got a common base. So common logs have a common base. So if I come up here and hit log, that means that would be 10 raised to that power would give me that same number. Huh?
It is the log first.
Yeah, it depends on whether it's what we call, used to call it reverse Polish or standard entry. So that's the name it got. So what is common logs? Common logs is nothing but what 10 would be raised to represent that number. Now I can start rounding this off. Now if I start rounding it off, I'm gonna still have a pretty good idea what my original number is. So here's my original number. I'm gonna come back and raise 10 to that power, and that's the original number. Okay, so somebody write that down. 12,587. Are we okay? But look how many digits that it took to get me that exact. But what if I come over here and I say 4.1, and then I raise 10 to that power? I come up to almost the same number. It's not as accurate, but now I'm representing it with less numbers. Y'all understand that? But it's still close enough for communications because we deal with so many approximations anyway. So normally what we would do is we would round these bells off. Everybody okay? To convert, so just raise 10 to that power. Normally on a calculator, you'll notice, if I didn't close my calculator out, normally your 10 to the power key and your log key are usually right next to it. Sometimes they're actually the same key. You have to hit a shift. So you'd shift to get the log. Now these are what we call common logs. Natural logs is 2.73 raised to some power, and we don't even need to worry about that. If you was in math, you would understand why. Or physics. Physics, you'd use common logs, natural logs sometimes. Are we okay? Now you know dB. So 2.56 bales, and then so that would be equal to that number, right? You understand? But as soon as we start rounding, we start getting some of our accuracy. So what will be the actual bale of 2.4? What would be the actual number for 2.4 bales? You just hit 10 raised to that power. So notice my calculator down here has a 10 raised to that power. So I'd enter 2.4. And then I would hit 10 raised to that power, and it comes up and gives me 251 point something. So to get the actual number, we raise 10 to that power. To get the bales, I just hit hit the log key, and that gives me the number of bales. Are we okay? And there's the whole answer. Are we okay? Relative power decibels are equal to bales times 10. Hence the name decibels. So here I would say this would be 24 dB. Instead of saying 2.4 bales, I would say 24 dB.
Broke it down.
Yeah. How many dB is 5.256? Well, it's 52.56 dB. Y'all understand? So I'd say, okay, I just multiply by 10. Multiplying by 10 is real easy. Multiplying by 10 and divide by 10 is real easy. So if I multiply 10, I just move the decimal point to the right one spot. If I divide by 10, I just move it to the left one spot. So this would be 52.256 D. We do a lowercase, uppercase D. That's decibel. Now that's not a unit. That's kind of like me saying milli. Right? You understand? Everybody okay? Now normally what we do is when we get to dB, we either round it to 2 letters or we round it to 1 decimal point, or we round it to 2. Very seldom do you see dB rounded to more than 2 decimal points. So as soon as I do that, I'm turning to an actual answer to an extremely close approximation. But what it does, it gives me to represent very large or very small numbers with very few digits. So it's just like in AC. What do we get when we start getting into DC? They say round everything to 2 decimal points. But when we get into AC and solid state, we say round to 1 decimal point, because now you start understanding that we're dealing with components that have tolerances, right? You understand? So we round. Your calculator rounds when it gets to engineer note, when it gets to scientific notation, but it still displays 10 digits, which is still a lot more than we need for the accuracy that we have to have in communication. Because everything that we talk about in electronics is approximations. Our resistors have tolerances. Our capacitors have tolerances. All this has tolerances. Our wires have resistances, but it's also resistance per 1,000 feet, which means that varies all over the place. And it's resistance at 20 degrees centigrade, which varies all the time.
So again, no perfect.
There's no perfect. Our math is perfect, but our components are not. So when we start getting into your advanced electronics classes, the maximum we're going to carry it out is 1 decimal. So dB is usually rounded to no decimal points, or 1 decimal point, or 2. Okay, that'll take a 10-minute break. So decibels.
Do we have a blocker in here? How works it?
Some of them, A buildings are bad because it's got a lot of metal. This building, I have no problem with this building. Nancy, her college phone don't do it, but her. I changed the slide a little bit too. So it's either going to be no, right, decimal points, and you'll see this done a lot. I don't know why I didn't put that. So I need to space this over a little bit so it's drop down. So either they're either going to use no decimal points, or they're going to use 1 or 2. Like I said, you might see 3, but I've never seen more than 3. Because what we do is all we're trying to do is get an approximation anyway, right? So convert these are bells, convert those over to dB. What y'all got? Should be able to do it in your head. 15.6. 122.3. 1.35 and 58.56. Okay? James? Just move the decimal point to the right once. Yeah, just move it to the right. So all you have to do to multiply by 10 is just move the decimal point to the right, and you can do that in your head. So just go whoop, you go whoop, and you go whoop, and you go whoop, and now you got dB. This is decibels. So this would be what, 15.6. But now you got to put dB. Yeah, and this would be 122.3 dB. This would be 1.35 dB, and this would be 58.56 dB. Huh? This is the way we would represent gains or losses. By the way, on your calculator, let's put, just for the heck of it, let's put -3. And do 10 raised to the -3. So on this calculator, it looks like I closed out my calculator. Should have came up with minus bells. So I'm gonna put -3. Now, by the way, In DB, we don't use engineer notation at all. We don't use scientific notation. We use the term 0.3 or something like that. But what I want you to do is this is a minus, and I'm going to take the log of that. And notice you get a fractional bale. See that? So you get a fraction. So if your decibels, I'm sorry, I'm gonna say minus. I didn't do that right. I didn't want to do that. I'm gonna clear that. That's not what I wanted to do. So I'm gonna put minus 3, and I'm gonna take the log of that number. Log.
Math error. So,
What are we doing wrong? Oh, it's not a negative. I'm sorry. I'm gonna come up here and say 0.3, and I'm gonna take the log of that. Notice, what does it do? It gives me a minus number or negative number. So right off the bat, if you see a negative decibels, you know it's an attenuation. If you see a positive, you know it's a gain. You understand? Scientific calculators have a log key. Y'all all found the log key on your calculator, right? And then you've got somewhere on there, you got a kin to the X key. Yeah, but somewhere. Yeah. So somewhere you got a 10 to the X option on your calculator, and somewhere you got a log option. Now what you need to make sure, it's set up for common log. Because if it's set up for natural logs, you're going to get wrong everything. And of course, you can check it. If you hit 10 and hit the log key and it come up and says 1, you're fine. So that's a quick way to check without seeing. Normally they display it on the top. Scientific calculation, once the number has been converted to bales, multiply the number by 10 to convert to dB. But you got to understand, to multiply by 10, you don't have to use a calculator. You just shift the decimal point over. You can do that in your head. Right? You understand? Change the one, yeah. A system has the following power gains: 247, 567, 0.34, 45, 0.67, 0.7. What we've done is we took the log of it. So the log of 247 would be 2.39, and then I come over here and I convert that to dB. Right? You understand? The log of 567 would be this. I convert that to dB. Log of 30.34, but this is 0.34. Now all of a sudden my dB is minus. So right off the bat, I know I'm getting less out than I put in. Over here I'm getting more out. Here I'm getting less out. Here I'm getting less out. Everybody understand that? So if you have a minus dB, it means it's a attenuation. If you have a plus dB, it means it's a gain. So here we got all these things right here, and these are all gains. So if I wanted to calculate this, I'd have to get out my dang calculator, and I would have to add them up. Okay, so I would come up with this gain right here. So my gain would be 1,105,444.57. But what do we have to use? Here we have to use a calculator. And over time, by the way, you get a feel of what power tens are. Now let's use dB. So dB, I would just do what to all these? No. I just add them up. I just add them. So that's the way you multiply exponents. The way you multiply with exponents is you just add the exponents together. So all I'd have to do is just take all these dBs and add them together. So when I'm giving you losses in a communication system, I'm not going to give you a number. I'm going to give you a loss in dB. But if you knew how many loss you had in your cable, if you knew how many loss you had on your transmitter, you knew how much loss or gain you had in your amplifiers, all you got to do is just add those dB up, right? You don't have to even get out a calculator. Now eventually you are, because now we need the actual number. So I add all these up and I get, we have an answer of 64.44 dB. That would be the entire system, right? You understand, my entire communication system. Now I need to know that actual number. Well, in my head, I would come over here and I would shift this over 1 decimal point, and then I'd raise 10 to the what? 6.044 power. That's what I would do. Now, of course, I've got to have a calculator, but in my head, I have a pretty good idea what 10 to the 6th is. I know it's going to be somewhere between 10 to the 6th and 10 to the 7th, right? So I basically, most people can do powers of 10s in their head. So 10 to the 6th is 1,000,000, right? Y'all understand that? So this is going to be this number right there. Now notice the two numbers are not the same. But what did I do? Well, I did rounding, but they're still close enough for what we call a very accurate approximation. But now most of the math I can do without a calculator. So what's nice about exponents is that to multiply your numbers, you just add your exponents together. Here they all have the same base. In math, you're going to say 10 to the 3rd, and you're going to say, well, I'm going to have 5 to the 6th. Well, the first thing you have to do on that is you have to get everything to the same base. So to add exponents together, back in algebra, you have to get everything in the same base. But in logs, the base, all the numbers have the same base. So it means if all the numbers have the same base, all you got to do is add the exponents together. And we do dB so often in logs that you've got 2 keys on your scientific calculator that lets you do that. So if I hit the log key, that gives me the bells, right? You understand? But how do you go to dB? So what dB does, it allows us to round the numbers, what it does, and still be pretty accurate. Y'all understand that? So I could round these to 1 decimal point. So I would say, okay, I could use, up here I'd use 24 dB, then I would use 28 dB, then I would use a minus 5 dB, then I would, this would be 17 dB, this right here would be 2 dB, this right here would be 1 dB, and I could add those up. Now, of course, the more I round, the less accurate my answer is going to be, but it's still going to be accurate enough, right? You understand? So when we get into communications like wires and stuff like that, they're going to give us a 2-digit or single-digit dB. And of course, odds are it's rounded, but it's going to be close enough so I can tell if I'm expecting a 3 dB loss and I get a 15 dB loss, right? You know we got problems. If I'm expecting a 3 dB loss and I'm getting a 2.4 dB, I said everything's okay. Because these dBs are going to be rounded, right? You understand that? It's just like when we get into engineer notation, you know, you get into some numbers, they go on forever. So do 1/3, right? It's going to be 0.22222. Well, sooner or later, you're going to start rounding. But as soon as you start rounding, then when you convert it back, you're going to have a slight error. But it's still going to be close enough to know if you've got a problem or if you don't have a problem. Right? You understand? So if it's within the dB that I calculated, then it's okay. But if it's twice the dB or something like that, then I know I've got a problem somewhere in my communication system. So basically, it's a lot like we use engineer notation, but unfortunately, guys, this is not what they did because we adapted this over from voice communication, right? So we started sending voice over these telephone lines, and voice varies in decibels. It don't vary and so when we moved into communications, it just seemed natural instead of using engineer notation, we just moved into dB. So the Bell company or the telephone company was was trying to figure out a way they could calculate how much volume you would lose over a distance. And unfortunately, sound does not vary linear. Your ears are not linear. It varies in decibels, right? You understand that? So it makes sense. Power is the rate of doing work. Voltage is the difference of electrical potential that causes current to flow. The formula for voltage is this. Now the problem we have, guys, is that every media has what we call a bandwidth. And anybody know what bandwidth is? Hopefully that's in that. It's in that glossary. But you hear it all the time. So you're networking. You have so much bandwidth. You got so much bandwidth. You buy a phone. You got so much bandwidth. Well, what the heck is bandwidth? Right? So you just know the more bandwidth I have, the better I'm doing. It's just like data. So I go out there, and when you buy these plans, they have set rates. They have, okay, I'm going to give you 8 gigabits. Well, most of y'all don't even know what a gigabit is. All you know is that gigabytes, or gigabits on data rate. You don't have no ideas. You just know the bigger it is, maybe the better it is. But here I was, when I got my cell phone, some of y'all are getting 16 gigabytes of data and stuff like that, and you're paying out the butt for it, but you don't actually go and look and see how much gigabits you're using. So I realized, by George, I had 8 gigabits worth of data I could send, and I'm on Wi-Fi so much. Everywhere I go, I got Wi-Fi. And I started looking, and every single month, I'm using less than 1 gigabyte worth of data, and here I'm paying for what? 16. Oh, I was paying for 8. That's what came with the phone. So what did I do? No, I didn't. I just called up and reduced mine down to 3. I figured 3 was a good enough margin. So now my cell phone bill went down a lot because I did what? I looked at what I got. So all y'all know is bandwidth. Bandwidth, well, heck, what's bandwidth? Well, it means nothing unless you know what bandwidth you're using and what bandwidth is. So what is bandwidth? What's it say? It's the range of frequencies a media can pass. Now, what's media? Well, media is what information moves through. So media is what it moves through, and bandwidth is the range of frequencies that media can reliably pass. Now, what do we mean by reliably pass? What are we trying to get through? We're trying to get through power. Even though it's information, we still got to move power. We still got to move voltage. We still got to move current, right? You understand? So your dB loss is going to be signal loss, right? You understand? But signal loss, most of the time your signal is going to, what 2 ways do we send signals? Basically, we got one primary way we send signals. What do we use to send signals? We got 3 things we can use. We can use current, or we can use voltage, or we can use resistance. We can't send resistance. So we have 2 primary ways we send information. We either send it we vary the voltage levels, or we vary the current levels. Which is the most popular way to do it? Voltage, yeah, voltage. Voltage is easy to receive. Voltage is easy to translate back over. So I send this power, most of the time we send it at voltage. Of course, fiber optics, we send it with what? Light. So voltage. But I'm trying to get power. So what we got to do is we got to understand the relationship between voltage and power. So right now I can say, what happens when we double the power to a circuit? So what happens when we double the voltage to a circuit? What happens to power? If we double the voltage to a circuit, power goes down. What happens? If I double the voltage to a circuit, what happens? If I double the voltage applied to a circuit, what happens? So if I asked that class in DC, I could almost guarantee, I said if I double the voltage to a circuit, I almost guarantee everybody say the power would double, but that's not true, because what you have to understand is I is equal to what? What's I equal to? V over R. Well, if my resistance don't change, if I double my voltage, my current doubles. Okay, but power is equal to V times I. If I double my voltage, my current doubles, my power is going to vary with the square. If I half my voltage, my current's going to half, and my power varies with the square. If it goes down, it's 1 over the square. If it's goes up, it's the square. So if I double the voltage, the power is going to quadruple. If I triple the voltage, my power is going to go up by 9 times. If I half my voltage, my power is going to drop down to 1/4. So power varies with the square. Power varies with the square of the voltage. So what does that mean? Well, that means I can't look at the voltage across. So let's look at this. 10 volts causes 10 amps to flow. So that gives me 100 watts. If I half the voltage, then what's going to happen? So here we dropped it down by what? If the voltage applied to the voltage triples, then if my voltage triples, my current triples, my power went up by what? 900 volts. That's why we're very concerned with voltage. Because if my voltage halves, I think I tell the story about my mom and her stove. Well, it wouldn't boil water anymore. Her electric range wouldn't boil water anymore. Well, she lost one of her feeds on her 240, so her heating elements was only getting what? 120 volts. Well, the power dropped down to a quarter of that. In communication and power systems, we are very concerned with the amount of power produced or delivered. Power gains and losses is very important to measure because it is voltage times current. Voltage gain and loss is very easy to measure. In a circuit with 10 volts applied, 10 amps, we get what? 100 watts. If the power is half, if the voltage is half, what happens to the power? It drops down by 1/4, right? Everybody okay? Notice the power decreased by 1/4. If the voltage applied to the circuit quadruples, then the power is going to go up by 16, right? You understand that? Everybody okay? Now this is the trick. On the previous slides, okay, if the power drops to 1/3, if the voltage drops to 1/3, what happens to the power? It's going to drop by 1/9, right? Okay. In circuits producing 25 watts of work, what happens to the power in a circuit if the voltage increases by a factor of 4? It's going to be 16, right? If it decreases by a factor of 5, it's actually going to, if the voltage decreases by a factor of 5, your power is going to be 1/25. Y'all understand that? Okay, well, okay. Okay. This is the problem. This is the trick. So what if my power drops to 1/2? So the way we measure bandwidth is we measure power. So when the power drops down to 1/2 on each side, then this would be what we call F1, this is what we call F2, and your bandwidth is going to be equal to F2 minus F1. And that's what bandwidth is. But power is real hard to measure. What can we measure? We can definitely measure voltage real easy. So what I need to do is figure out what the relationship between voltage and half power. Y'all understand that? Okay. So let's do a little math. What I'm going to do is I'm going to come up here and I'm going to say we'll say my power is equal to 10 amps times 10 volts. This is going to give me 100 watts. Now what I'm going to do is if I decrease my voltage by 0.707, now we're rounding, it's actually the reciprocal square root 2. Yeah, and we run into 0.707 a lot. Well, if I drop my voltage down to 0.707, my current's going to drop down to 0.707, and what does that give me? If we didn't round, it would give me 50 watts. So that means if I can measure when my voltage drops down to 0.707 here, so if I know my maximum voltage I ever get, that's the maximum voltage we get. And then I can measure where my voltage drops down to 0.707. This is, let's take away the power. And it pops down to 0.707 right here, then that's going to be the half power point relative to voltage. And a lot of people say, okay, what would the voltage be if the voltage drops down to 1/2? Everybody wants to think the power is going to drop to 1/2. So this 70.7% of voltage or current, because current and voltage are proportional, right? You understand that?
Yeah.
But current is not easy to measure either, because to measure current, to truly measure current, what do we have to do? We have to break the circuit and make the current flow through the meter. We can measure voltage with the power active. We can measure voltage just by taking and measuring across the lines, right? You understand that? Well, if I've got 10 volts, then I'm going to get 100 watts of power. But if this voltage drops down to 7.07, then I've just hit the wall. I've hit the half power point relative to voltage. That all just makes sense. Relative to voltage. So the range of frequencies between 70.7% of my maximum voltage, that would be the half power point. But now we're doing the half power point relative to voltage and not relative to power. Because to measure power, we got to measure two things, right? You understand? We got to measure what? Current and voltage. So that power meter on the side of your house is actually measuring two things. It's measuring what? It's measuring voltage and current.
That's the RMS value.
For AC, but it's also the half power point. So we'll run into this 0.707 a lot. But what's neat is you can do the math and you can see that if I have so 10 times 10 is real easy, because 10 times 10 is 100. And then we do 7.07, which would be 70.7% times 7.07. And it comes up to be 49 point something, because what are we doing? We're rounding. Okay, we're okay? 70.7%? Okay, we got one more thing. Now, when we do it according to logs, we're interested in power. But remember, voltage varies with the square. So dB would be 10 times a log of power. Now, this is the formula. But on most of your calculators, if you've got a standard calculator, you've got to enter this backwards, right? You understand? So anybody that's worked with a standard entry calculator, if you got a formula and you got parentheses and all this stuff, you have to work backwards. So the way we would do this on our calculator is we'd take P out over P in, then we would take the what? The log of it, and then we'd multiply it by 10. But if you ever look at the formula for dB, it's going to be 10 log out over N. But this is power. What would that be on voltage? So if I took 10 to the first, right, you understand? And then I multiplied that by 2, that's going to get 10 to the second. And this is going to go from 10, this is going to be 100. Well, what I did was just square that number. So what we can do is my dB, and this would be power, could equal to 20 log V out over V in. And now what we've just done is we've calculated the power loss. or the power gain. You understand why? We're using volts here because we can measure volts. But when I talk about my bandwidth has nothing to do with volts. It's power loss. But what we got to do is we got to get power loss relative to voltage because we can measure voltage. Even on fiber optics, if I've got a transmitter that can generate a certain voltage, and then I receive that light, and that light is converted over to a certain voltage, then I could actually measure voltage loss in my transmitter and receiver and get what we call a power loss. I can get a light loss through the cable, right? You understand that? But what we have to do is we have to get this relative to something I can measure. Power we can't hardly measure. But we can measure what? We can measure both. So what we got to do is say, well, voltage and power varies with the square. So if I can measure my output voltage and measure my input voltage, if I can take V out and divide it by V in, then I take the log of that, and then I multiply by 20, that gives me my power loss. Huh? Well, around. It's going to be an approximation because we're going to round some of it, right? So power loss relative to voltage is we multiply by 20. Power loss regular dB loss, dB relative to voltage is we multiply by 20. dB relative to power we multiply by 10. Do y'all understand why? Power varies with the square of the voltage. So what you're doing when you multiply by 20, you're squaring the answer. So what you're doing is you're getting the power gain. But I'm not getting the power gain or power loss using power. I'm getting the power loss or the power gain using volts. What can we measure real easy? Volts. So my gain or loss relative to voltage would be this formula. Relative to current would be the same thing. So it'd be 20 log I out over I in, but we don't use that much either because to measure current we have to measure what? We usually have to break the circuit. So voltage is real easy, but you got to understand. But what are we concerned with? We're not concerned with volts. We're concerned with power. Why? Because power is this. Power is work. I'm concerned with how much work I'm losing. I'm concerned with how much. So when I deal with voltage, I can use what? I use dB is equal to 20 log V out over V in, right? And if whatever I get, that's going to give you the power. That's going to give you the power loss, or it's going to give you the power gain. This is why dB is so popular, because dB, when we start dealing with communications, it's real easy for me to get these losses. So if I've got a voltmeter on one side and a voltmeter on the other, and I measure that loss, I can do it. I can calculate the power loss, right? Not the voltage loss, the power loss. So Alabama Power talks about, line loss. They're talking about voltage. But remember, for every volt they lose 2 watts of power, right? You understand that? For every volt, because it varies with the watt. It varies with the square. So 20 log. So this is what we use a lot on electrical communication. So when we start talking about losses in a communication system, they're going to be given in dB. Okay, guys. Let's see y'all. Yeah, you know what I just found? No. What I need to do is swap these around. Well, no, I just need to put my power. That's just me. I got to do that.
I noticed in the room over there there's some robots.
Yeah, Albert started putting them together.
Yeah. Did he get any done?
I don't know. You could do that. Well, I come back tonight, so.
Come back tonight.
Just thought stay. So it's up to you. You could work over there if you want to. Just keep up with your hours. Yeah, on Tuesdays and Thursdays. Since I come back, and you're more than welcome to do that. She just said if you leave early, you need to keep up with your time and just make. So what I'll do is I'll lock the door when I leave. But if you go outside to smoke a cigarette or something, you're gonna have to put something in the door to keep it from closing.
Let me see if I can get some